I am going to come up with a new programmable architecture, which I am going to be calling a field programmable gate array. Here's what I'm going to do. One of the things that sucks about the old CPLD is that you're limited in the way that the signals route. Okay? So if you look at the way that it's routed, it's like you can do a whole lot, but it's like it's really weird that you have to you can come in, you can only access some logic, then you have to come through here and go back over there. The interconnection in itself is a pile. Okay? So what I want to do is I want to create a new architecture that does the following. I'm going to have logic, programmable logic, and it's going to have these little blocks, okay? And it's going to have all the stuff that I want. Okay, it's going to have, the combinational logic circuit. It's going to have the D flip-flop. It's going to have the multiplexer so I can do whatever I want to do. But I want to address this whole issue of interconnection. So what they did is they took these logic blocks, and they put them into an array, and then they created these programmable interconnect routing switches all over the place, like tons and tons of them, so that you could get from any logic block to any other logic block and back by routing through these programmable little switchboards. Okay? So this changes everything. In addition to doing that, what they did is they have these programmable input-output blocks that sit around the outside, and they had made it so that any pin could be an input or an output. Okay? So the interconnection is what the magic of an FPGA is. Okay? All right, so life is good. I feel so good that I have this now. So what do? Let's take a look at this guy. Let's take a look at the logic. Because they decided that they didn't really like this whole sum of products. They came up with a different way of actually creating that. And so let's go into this thing and look at what it is made of. Okay? The first thing I'd like to highlight is it's got two different names that you'll see. Okay? It can be called a configurable logic block, or it can be called a logic element. And you go, why is there two different names for this? Well, Xilinx came up with configurable logic block. Altera calls the little blocks logic elements. Okay? Same exact thing, but it's just two different terms. So what's inside of a logic element? It's exactly what you would think. You're going to have the equivalent of a PAL, and I'm going to put a little tilde in front of it. Kind of a PAL. All right? Not quite a PAL, but we'll talk about that in a second. But look at what you have to do. You're going to have a multiplexer and a D flip-flop, and you can do exactly what you could with the original architecture. You can have the combinational logic feed into a D flip-flop if you want, and then you can have it also feed the output, and you're going to use a multiplexer to choose. You can also program the logic to be just a wire and make this entire thing a D flip-flop. But they decided to use a different technology, okay, to implement the combinational logic. And it is called a lookup table or a LUT. Okay, so when you talk FPGAs, people always be like, how many LUTs you got? And you'll be like, 100,000. And the other guy's like, cool. Okay, so you're talking LUTs. This is the terminology that we're used today. Now, what is a LUT? Okay, well, a LUT it's a really simple and ingenious way of implementing combinational logic. It is nothing more than a multiplexer. Okay, but what's funny about it is that instead of programming like the interconnections in order to form the logic, they say, you know what I want you to do? Just tell me what the output is. And I will put it into memory, and I will put it as an input into the multiplexer, and then I will choose whatever output. If I had a truth table that was 0001, 1011, so a traditional two-input logic circuit, and I wanted to implement 1001, I would come over to a multiplexer that has 4 inputs. And the 4 inputs would receive the outputs that I have implemented in my truth table. These are implemented in memory. So you actually put these into memory, and they're routed to the inputs. And then think about what happens if you drive A and B into the select lines of the multiplexer. It goes out and chooses one of these 4 rows to drive to the output. That is a combinational logic circuit. Isn't that sweet? It's pretty ingenious. Okay? Why is it called a LUT? Well, it's a lookup table in the fact that you start with a truth table and you provide essentially the address of the row that you're going to go look up the output. Okay? Now this is sweet. This is what we have on our FPGA in the lab. It turns out the double EEPROM went away because it was a little bit too slow. So they changed the memory that holds all of these little pieces of information in an FPGA, in addition to all the routing and all the stuff on there, and they use a different type of memory. What would you guess is the memory that we hold our program, or our hardware program for the FPGA? If you were to guess, I'll give you a hint. It's one of the memories we've talked about in the chapter 10. SRAM! It is SRAM. It says right there. That's an awesome way to roll that out, okay? All right, so it's SRAM. Now, what does that mean if you use SRAM to hold the hardware configuration? Have you noticed anything about the lab when you turn the power off? Your program that you worked so hard on is gone, okay? That is how FPGAs are today, okay? They use SRAM for their configuration, and when you pull the power, what happens is it's gone. They do that because it's very fast, and it's not so much fast as it is efficient to store those little bits. Because if you have a double EEPROM in those little bits, it takes up a lot of room. Use SRAM, they're tiny, okay? But if you're going to have a system, you can't have every person download Quartus and you sell them a product and then you're like, well, just compile this code and then download it. No, nobody's got Quartus, okay? You guys are like the only people in the world that have Quartus, okay? What do? You have to have a non-volatile memory, okay? So a typical system that has an FPGA will have an FPGA and a double EEPROM or flash, and the first thing that happens is when you boot up, that flash holds the contents of the program that is then, on startup, downloaded into the SRAM of the FPGA, okay? So the SRAM is great when you're prototyping because you're just sitting there programming it over and over and over, but once you get ready to do a product, you have to put that program somewhere in non-volatile memory. If you notice, now I don't know how much you've messed around with the boards. When you power up that board, does it have a program on it still? Okay. Does anybody use a board that doesn't have it? Okay, cool. That's good. Sometimes people notice that when you go out on the programming chain, have you ever noticed that multiple programmable things come up? Does anybody notice that? Yeah, one of them is the double EEPROM. And sometimes people can try to program the double EEPROM and they blow away that default program that's on the board. So over time, those programs that come on the DE0 board will get blown away. Okay? But if you come to a point where you're going to do a senior design project and you're like, I need something. I need to build a thing, put it in a box, and it needs to hold its thing, okay, to hold its program. You have an FPGA in there, you're going to throw a double EEPROM, okay? Guess who sells double EEPROMs that are made to program FPGAs? Xilinx and Altera. Okay, they actually said, give me that stuff, I know how to do this, and they make these chips that are specifically designed to interface with them, and you just wire them up, it boots up and programs, and it's a piece of cake. It's awesome. Okay, let's take a little bit of a look at this lookup table, because it's a really cool idea. Let's see here. You know what you could also do? One of the problems with this is this would be a 2-input lookup table. Does that feel good? But you're not going to be able to do much with a 2-input lookup table. You're going to need your 3 inputs, your 4 inputs. Probably immediately you're at 6 inputs. Okay? And it turns out that modern FPGAs have like 6 inputs, some have 8 inputs. So you'll say, I have an 8-input LUT. If you build this multiplexer, it gets really big really fast. So one of the things that happens is that they actually will build these lookup tables using 2-input muxes, and they form it into like this. It's almost exactly like a binary decision tree, where based upon the inputs, you essentially route the original output through the set of muxes until it gets to the output. Okay? So in our example before, I could build that 4-input mux with 3 2-input muxes like this. And if you think about it, you could actually look at how they're routed through. You always put the most significant input as the last mux, the final mux. And then you think about it, if you look at the truth table, if A is a 0, it's going to choose between 2 of these inputs. And so immediately this mux chooses this mux, and then B is used to choose between these 2 inputs. Okay? So it's essentially a binary decision tree. How's that feel? You know those interconnections that are so cool that we use to program the routing from input to output? It turns out that they have a pretty cool little way to do it. They do it with just transistors that are opened and closed, and I drew out kind of all of the ways that they look. They're called PIPs, okay? They're called Programmable Interconnect. Well, it's FPGA, blah, blah, blah. Okay, think about this. You have a transistor, and it's got an input to tell it whether it's open or closed. So if it's an NMOS, you just have this on the gate. Whether it's closed or open is dictated by another SRAM cell holding the information. Okay? And if you think about, you put this huge array going every which way, and what they do is they put these little programmable interconnections in this configuration right here. Okay? And so when something crosses, they put 1, 2, 3, 4, 5, 6, and they can actually get any and all possible directions and connections by using that topology. Okay? So it's pretty simple, but it's pretty clever. This is all facilitated by being able to put a ton of transistors on an integrated circuit. You could have built this in 1970s, but you would have only had like hardly any logic at all. This FPGA approach, you are putting so much logic down to facilitate the flexibility that you guys have. It's only practical when you can put down a billion transistors on a chip. Okay, so this is why it took until today to have this really cool capability. Okay, all right. In the FPGA also is going to be the input-output block. Now this is a really cool thing. If you think about the original FPGA, those logic elements, they were one direction. Okay, they had inputs and they had an output. They had a D flip-flop in it, and that's how you make your final state machines. But on the pins themselves, one of the things that they ran into was that if you're going to have something come into the FPGA and go into a D flip-flop, it takes forever to get into the D flip-flop internals because it's going through so many switches. So they said, if I really want a fast system, I should have the D flip-flops right at the output pins, okay, so I can control the timing. So what they do is every input output pin actually has a circuit next to it that you can tell to have a D flip-flop on both the outputs or the inputs. That's beyond what we do in this class, but if you start working in a lab or working for a company and you're like, man, this thing just is slow, I can never meet the setup and hold specifications of the D flip-flop, this is what you end up doing. You start using the D flip-flops right on the pins of the device. Okay? How's that feel? Feels so good we should just stop.